All right, I'm going to call this example 3, I think, from the notes. I think that's the order. This is a 2-part problem. I think it's from an older beer, Johnston. I've also done this example in a previous lesson, one of the other links from one of the other years. So check that one out. This one I'm going to do by just revealing pre-made images that I have, so it'll go a little bit faster. So in this situation here, they give us sort of a generic picture, and they tell us that this 80 millimeter radius wheel is going to rotate to the left with a velocity of 900 meters per second. When they say something like that, they mean it's the center, okay, that's moving at that speed. And we know these lengths of things. Let's see, they say AD, so that's the position between this point and that center is 50 millimeters, whereas the radius of this is 80 millimeters. And they want to determine the velocity of this collar and the angular velocity of the rod, AB. So, and the first scenario they have is this beta. This right here is going to be 0. So when you have something like this, it's really good to redraw this position, the sketch in that position. And so here I put those in there, and I also, in doing so, I also calculated what this angle is going to be as 31.33. So that's taken care of. It's really good to try to summarize all these positions, make a good sketch. So we want to use the 3 position or the 3 diagram method for this. Here I've put them in. And we're going to do this because we, in this, we know this is going to rotate, and we can assume it's not going to slip. They would have told us if it was going to slip. So we could have these 3 points, D, A, and then E is what I'm calling the point where this disc meets the ground. If I write out the equation for the velocity of E, okay, because that's the special thing that I know of. I say the velocity of E is going to be equal to the velocity of D, right there. And I didn't actually write this on here, so it probably would have been better if I had been thorough here. But velocity of D, that's the reference thing that we know, plus the velocity of E with respect to D. Okay, and so because D is the thing that we know, so we know this velocity is going to be 900 millimeters per second, and the velocity of E with respect to D that's shown right there is going to be, or the speed I'll say, because we want the magnitude, is going to be the omega. What did I say? I guess I just got to call it DAE. I usually put them in alphabetical order. Times, and let's say it's R, and that's going to be E with respect to D. I'm writing with the laptop up right now. That's why my handwriting is so terrible. I'm sorry about that. It's difficult to write this way. I was trying to save some time, and I've just caused more problems. All right, so that's right here. I've just written shorthand right there that omega DAE times 0.8, right, because it's the 80 millimeters. And with that, we're able to find the angular velocity. Quite often, that's going to be one of our strategies. Look for that as an intermediate step. Quite often, is to piece together some way that we can find this the angular velocities of a rigid body, and then we look at rod AB, and as part of this. Okay, so when we're looking at rod, the way we've drawn this up above is sort of telling. right? From how we've drawn this disk, we can also take a look at what's going to happen at A, right? We could have written that as a separate equation out there. So what is the velocity of A? Well, it's going to be in a straight line right here, right? We could recognize that if we write that out separately, the velocity of A is going to be equal to the velocity of D plus the velocity of A with respect to D, right? And we go across and we look, well, D is completely going to be in the horizontal direction, and the velocity of A with respect to D right here is also going to be completely in the horizontal direction. So our conclusion is the velocity of A must be completely in the horizontal direction. Okay. Next, we come down and go to the rod AB and take a look at the velocity of A. It's completely in the horizontal direction. Velocity of B up here at this collar, it too has to be completely in the horizontal direction. Our conclusion is that this rod does not rotate, so its angular velocity is actually 0. Okay, and so it will just be in complete translation. It's kind of hard to picture. If you don't believe that, that's fine. It's totally normal that you would question, why? Wait a minute, it seems like it should be rotating. Well, in the 3 diagram method that we have here on the bottom, we go ahead and do our piece here where we're going to say the velocity of B is equal to the velocity of A plus the velocity of B with respect to A. And we take a look, and it's this last diagram that kind of can make us convinced that there can't be any angular velocity, because if there is, it's going to have a vertical component right here, and we know that B can't have a vertical component. A doesn't have a vertical component. Therefore, the only way that this can be true is if the link AB, the rod AB, does not rotate. So that's the conclusion. The rotation is 0. And therefore, we can find the velocity of B is going to be equal to the velocity of A, which I don't think I actually calculated anywhere. I think it's actually missing from this. So I think what you would need to do to find the velocity of A, so I for some reason didn't write that thing out, so shame on me. The velocity of A right up here is going to be that 900. Let's just go ahead and use millimeters for a second. 900, all right, that's writing out this guy right here, minus, right, because this thing is rotating counterclockwise. That's what we decided, right? That's rotating. So that's going to be 900 minus, right, the that 11.25 times, and I used meters up here, but we were using millimeters per second, so we could just multiply that by 50, right? So 50, and what we have for the velocity, therefore, is 900, 11.25, and 50 times, subtracting, we get 337.5, which is in millimeters per second. So we can see that definitely we have the velocity to the left of 337.5 millimeters per second, and so that's the answer down below. If we do the same problem, but we're doing part B now, we want to make sure that we draw this thing out. Okay, so that when this beta is equal to 90 degrees, this is the orientation of this piece. And now we want to draw out the 3 diagram method again. And if we do this, we still have that scenario that we had over here when we decided that we were able to find the omega DAE. And it turns out that same scenario is once again true, right? Where E is going to be stationary. So if this thing has the 900 millimeters per second moving this direction, this thing has to have an angular velocity of 11.25. Right. So if you want to find the velocity of A right here, you need to write out, and once again, I probably should have written out the vector equation first, that the velocity of A is equal to the velocity of D plus the velocity of A with respect to D. Hopefully from repetition here, this is starting to seem normal to you. And then you do this in the X direction. And just keeping a generic VAX, even though I drew an arrow up here, I probably should have drawn it as this way and that way, right? So that was the VAY, and this is the VAX of the thing. And putting the values in there, you could see, well, the only thing that's going to happen in the X direction here, because if you take a look at this rotation right here, the rotation of the VAD is going to be completely vertical right there. So our conclusion is the horizontal component of A is completely translation right there. And then you do it in the Y direction, and you'll see that there is no component right here in the Y direction, but this is completely, so it's just that 11.25, and I use these as meters per second, and we're able to get this, and so we know that it's going to be upwards. So now we can take a look at rod AB, now that we have the velocity at A. And so we have the velocity of A is coming up this way. We know the velocity of B is going to be completely in the horizontal direction, and we can kind of guess that it's going to be to the left, but a lot of times we don't actually know that, by the way. So we want to be careful when making that guess. Sometimes it's just good to draw this as a dashed line through here and leave it unknown. So we write the equation: velocity of A is equal to the velocity of B plus the velocity of A with respect to B. Right there, right? So we're using B as the reference. So yes, we're using B as the reference. So we're writing the equation for this part of the link. And in the Y direction, right here, we already have this broken down into Y component, X and Y components. So that's convenient for us. So we just take that 5.625 that we got previously, and there's nothing here in the Y direction, so that's nice. And so we get this component, but we got to be careful, really careful with these angles right there. That's a difficult part right there, is to we did get this angle up above, but we have to draw these angles in very carefully. And we can see that we get the cosine of that 18.66 that we found up above. And from that, we're able to get what the angular velocity of this link is going to be. Now, knowing that angular velocity, we can go for and write the X direction equation, portion, or X component of this equation up above. And we could say, we already know the answer, that it was negative 0.09 to the left. VB was something that we are looking to try to get, and then we take only the horizontal component of this, and we just previously just found that angular velocity. So we're able to find this, and we find that VB is actually going in, it is in the negative direction. Okay, so I didn't give it a negative sign right there, so that's why I have a negative here. And technically, I probably should have written this with a negative right there, because I drew it up. I drew it up here as negative, so it's better to be consistent that way. So anyway, here's another complicated problem that you want to work through and think through. These are things you need to test yourself with and to gain confidence. Just watching someone do the problem isn't going to be enough to be able to be good at solving problems like this. So I will discard all those changes, and we're done with a 14-minute example.